Hello everyone, my name is Khushi Undar and my ID number is 24CS101. I am from CSE department CSPIT, and in this video my topic is how digital logic is used in satellite navigation. We understanding the complete process from space to screen. So in this presentation we are going to talk about something that directly connect to our daily life. Whether you are booking a cab, ordering food online or trying to find your way to a new place, GPS is always working behind the scenes. GPS or global positioning system is what helps us figure out our exact location. But it's not just satellite doing all the works. There are actually an entire digital logic system powering it, and that's what makes it so fascinating. The title of this presentation is How Digital Logic is Used in Satellite Navigation. We will go step by step and see how the satellite sends signals, how your receiver decodes these signals, and what role digital logics play in that whole process. In each slide, I will explain in simple language how things like logic gates, flip-flops, counters, multiplexer, and other digital components work inside the GPS system. So let's start. So first of all, it's important to understand that what is satellite navigation. In simple words, it's a system that uses satellite to tell you your exact position and time, no matter where you are on Earth. The most popular system is GPS, which was originally developed by the US Army, but there are other systems too, like GLONASS from Russia, Galileo from Europe, and Pinduo from China. This entire satellite navigation system has three major parts. First is satellite, which are orbiting in space and constantly sending the signals. Receiver, which are present in your phone, car, or GPS. And third, most importantly, is the digital logic circuit, which process the signal and display your location on the screen. So today we are going to understand this whole process in depth. So next is role of digital logic in satellite navigation. Digital logic, which include logic gates, flip-flops, counters, and multiplexer, this circuit act as the brain of GPS system. They are the reason data is processed efficiently. For example, encoding the signals, transmitting it, and decoding and matching the data. And most important is calculating time, delay, and distance. It's because of this logic circuit that the GPS system works so fast and accurately. So in the next few slides, we will look at each digital logic component one by one and understand how it works on both the satellite side and the receiver side. So next is understanding how satellite system work. The first step is atomic clock, that accurate timekeeping in satellite. So this is a very high precision timekeeping device. It's a main job to send the exact time along with every signal. Using this timestamp, the GPS receiver calculates how long the signal took to travel from satellite to receiver. And this timing is so accurate that it can measure even tiniest delay down to nanoseconds. If there is even a small error in this, the GPS location would be incorrect, which is why the atomic clock is one of the most critical part of the GPS system. Now next is digital logic used in atomic clock. So the digital logic circuit that keep this clock running inside the atomic clock, there an oscillator that generates signal at a constant frequency. This frequency passes through digital logic components like flip-flop and counters, which help maintain the exact timing, and OR gates are used for timing control and plus zapping to make sure there are no glitches in the output. So in simple words, the atomic clock generates the time and digital logic keeps that time stable and accurate. And without this precise timing, the GPS system would not able to calculate distance at all. So step 2 is from satellite side. So the second component inside the GPS satellite is called the position register for satellite location tracking. The register stores the satellite's current 3D position, which we represent in the form of XYZ coordinate. Since the satellite is always in motion, this position keeps getting updated continuously. So now the question is, how does the satellite store its location? So next is digital logic used in position register. So for that it used digital register, and to hold the data inside this register it used D flip-flop. This flip-flop stores the satellite orbital coordinate, and a special control logic circuit updates them from time to time. Then multiplexer is used, which decides that data to send in the signal for the time or the position. When the signal is transmitted towards the Earth, it carries both the time from the atomic clock and the location from the position register. On the receiver side, this information is used to figure out that when did the satellite send the signal, and from where did it send it. Now let's move on the next step. So next is step 3 from satellite side is that how signal is encoded. So the main goal of this encoding is to combine the satellite clock time, position register and satellite ID into a single signal, so that when the signal reaches the receiver, it can easily identify which satellite the signal came from, when it was sent and from where it was sent. So this process uses basic logic gates. So is the next. So this process uses basic logic gates such as XOR gates, which make the signal unique, AND gate that which combine only the required data, and OR gate which prepare the final signal for transmission. This gets together from a digital encoder which convert the satellite raw data into a structured format. So now this signal is ready to be transmitted to Earth and through the next step, which is the satellite transmitter. So next is step 4, flip-flop and multiplexer data is equal to data holding plus combining. So let's first talk about the flip-flop. This act like a small digital memory unit. They hold data like time, satellite ID and location for just a few microseconds. This helps keep the signal stable and reliable. Next is multiplexer, which convert multiple data lines into a single line, just like a traffic signal that lets all vehicles pass through the one by one. Together, the flip-flop and multiplexer organize the signal with proper timing so that the transmitter can send it to Earth without any glitches. So let's go ahead to step 5, that satellite transmitter sending signal to Earth. So next is step 5, that transmitter sending signal to Earth. So let's start. Now the signal is completely prepared with the time, ID and location. Already the final task of the satellite is transmitting the signal. So the satellite's transmitter generates a radio frequency signal. This signal contains a precise timestamp and the current position of the satellite. The digital logic circuit ensures that this signal is sent towards to Earth at the exact right time with the proper strength, and all of this done using synchronized plus from the atomic clock. In the GPS system, usually 4 or more satellites send a signal at the same time so that our GPS receiver can receive multiple signals together. Now let's see what the GPS receiver on Earth does. It receiver this signal. Let's move to step 6, that receiver side. Now in step 6 we have come on the Earth side. And here the first component is the GPS receiver antenna. It capturing RF signal. This antenna captures the radio signal coming from the satellite. In the way it listens to the signal. The signal is very weak because it has come all the way from space, but it contains important information that location of the satellite and the exact time and signal was sent. The GPS receiver doesn't receive the signal from just one but from multiple satellites at the same time. Only then can it accurately calculate the exact location. From the antenna, the signal goes to the low noise compiler and analog to digital converter, which we will see in the next slide. So next is step 7 is a flip-flop plus XOR is equal to signal matching and storage. So in this, when the satellite signal reaches the receiver and it convert into digital form, it need to be held and matched. The flip-flop store each bit of the signal like a short-term memory, and then the bits are compared with the reference signal generated inside the receiver using XOR gate. The output of XOR gate is 0 when the both bits match. This means the satellite and the receiver are now aligned on the same signal. In other words, proper synchronization has been achieved. This process is extremely critical for the GPS system because without synchronization, the receiver cannot calculate the exact location. Here, flip-flop hold the signal and XOR gate compare it together. This makes signal decoding possible. So now next is receiver side. Step 8 is counter, that time delay measurement. Now when the signal is matched using XOR logic, the next step is to measure the time delay. For this, digital counter are used as soon as satellite signal arrives and the counter start counting clock pulses. When the signal and the internal code perfectly match, the counter stops, and this counter value tells us how much time it took for the signal to travel from the satellite to the receiver. Then by multiplying this time delay with the speed of light, we calculate the distance between the satellite and the receiver. With this simple step, the GPS finds out how far the receiver is from the satellite. So here digital counter play role of the GPS timer is as a fast, accurate and reliable. When we have so next is step 9 from receiver side is subtractor plus multiplier is equal distance calculation. So once we have the time delay from the counter, the next step is to calculate the distance. First we use subtractor, which subtract the satellite clock time from the receiver clock time. This subtraction gives as a delta t, the delay in the signal. Next, we use multiplier, which multiply the delta t by the speed of light is approximately in 3 into 10 raised to 8 meter per second. This is give us the accurate distance to the satellite. This whole process is done in real time using the fast digital logic circuit, where subtractor and multiplier perform the exact math with error free. The accuracy of the GPS depends on the logic gates. So now next is step 10 from receiver side is register that holding distance for temporarily. So now that the distance is to each satellite is calculating using subtractor and multiplier, we need to store all this distance so that the next calculation can proceed by smoothly and easily. For this we use register. Register are the kind of fast clock based on storage that temporarily hold the distance of each satellite. This data is continuously refreshed inside the GPS receiver. Usually every second, the register ensures that accurate data for each satellite is available at exactly the same time, so that the next step is triangulation can be done accurately. So without registers, signal synchronization and exact timing cannot be maintained. So now next is step 11 is also from receiver side is ALU and trilateration. So in this step 11, um, now that we have distance to each satellite, that all the distance are stored in register. So the actual task of calculating the location begin. This called is trilateration. The GPS receiver uses a mathematical method where the distance from 3 or 4 satellites are used to find a receiver exact 3D position in the form of XYZ coordination. This entire process is performed by ALU. ALU is that arithmetic logic unit. Inside the ALU, there are adders, subtractor, and multiplier, which work together to solve equation. And each satellite signal give an equation, and ALU solve this equation and determine where are you right now, at which latitude and longitude. So this entire calculation happened in real time, which is why your GPS update its location in every second. Fast, accurate, and glitch free, and with the all error free. So thanks to digital logic inside the ALU. So now next step and last step from GPS, to receiver side is that step 12 is decoder, and finally display logic and is that. So now once the ALU give us a final position for the receiver is in latitude and longitude is, and the next task is deliver this information to the user to display it on the screen. So this task is handled by decoder and display logic. The decoder converts the binary coordinate value into readable format, such as like a 28.70141. So they convert it into binary coordinate value. After that, display logic gets activated, which draw maps, markers, and navigation arrow on the screen. The smooth and real-time location you can see on your GPS on your screen by GPS system is the result of behind the scenes work of logic gates, display driver, register, ROM, and many digital logic circuits. So in today's smartphone, cars, and all the GPS system are use the same digital logic keys for real-time navigation. So now in this slide, we see the whole journey from satellite to your screen. For first is from satellite side. So first on the satellite side, the atomic clock generates precise time pulses, and the satellite exact position is stored in register. So to encode the data, logic gates like XOR or AND are used. Then the position register is hold the satellite current coordinate. Then logic gates encode the data into signal. Then flip-flop plus multiplexer is hold and organize the signal bits. And last from satellite side is a transmitter that sends and encodes RF signal towards the earth. So now from next is receiver side, and from GPS device is that sixth step is antenna that capturing incoming RF signal. 7 is a flip-flop plus XOR gate that store the and match signal pattern. 8 is counter that measure time delay in signal. 9 step is from receiver side is that subtractor plus multiplier that calculate distance to satellite. And 10 is register temporarily store all calculated distance. And 11 is ALU arithmetic logical unit that perform trial iteration using 3 plus satellite. And 12th and last step is decoder plus display logic show a real-time location on the screen. So now this is the whole process is the signal travel from space to screen. So in this video we learned that without digital logic there would be no signal holding, no distance calculation and no real-time navigation on GPS. Therefore we can say that digital logic is the silent hero behind the GPS system and working silently everywhere from space to our smartphones. So now next, thank you.